the autocorrelation and cross correlation, we continue our discussion of periodic signals, right. Last time we had looked at the autocorrelation and cross correlation function of aperiodic signals, and we realized that when we take the cross correlation of x with y, the Fourier transform is the product of the Fourier transforms of x and the complex conjugate of that of y, right. When we take periodic signals, we also saw what happened to the Fourier transform. The Fourier transform was a train of impulses located at multiples of the fundamental frequency. So let us just recall. We have two functions, two signals, xt and yt, both periodic with period t. Now, I must again emphasize the meaning of this statement, both periodic with period t. You see, it is quite possible that the fundamental periods could be different. For example, xt may inherently be periodic with a period of 2 units of time, whereas yt could be periodic with period 3 units of time. Even so, both of them are periodic with period 6 units of time. So, it is possible to find a common period. That is the issue here, right. It is possible to find a common period. And how do we find a common period? By taking the least common multiple of the period. So, therefore, if xt, the first thing is of course that xt and yt must individually be periodic. Let their periods be, let their inherent periods or let their fundamental periods be t1 or tx and ty. Then t is the lowest common multiple of tx and ty. And what do you mean by lowest common multiple in the context of real numbers? Well, lowest common multiple means that t is the smallest real number, positive real number, which is an integer multiple both of tx and of ty. That is what we mean by lowest common multiple for the context of real numbers, right. So, what do we mean? We mean it is the smallest positive real number which is an integer multiple of both tx ty. Right, and therefore we may write down t is m times tx is equal to n times ty, where m and n are positive integers. Z plus, they belong to Z plus. And therefore, it is very clear then that Tx by Ty must be a rational number. This is a necessary and sufficient condition for the existence of a common period. it is possible that there could be two periodic functions xt and yt with periods tx and ty which have no common period. That would happen if tx and ty have an irrational ratio. For example, suppose tx has a period of 1 unit and ty has a period of square root of 2 units, then there is no common period, right? And therefore, now why do we need a common period? Because we must be able to think of this function as periodic with that period. It does no harm, because all that it means is, you see, when you say a function is periodic with period 2, you are saying its fundamental frequency is 1 by 2 units. If you say its period is 6, you are saying the fundamental frequency is 1 by 6 units. All that you are doing is you are adding more frequencies to be considered, and many of them might be 0. It's quite possible that the component at the fundamental or the component at the second harmonic or the component at the third multiple of the fundamental can be 0. So you see, there is no harm in considering more points on the frequency axis. You know, that's what happens when you take a larger period, a multiple of the fundamental. So you see, the point is that we can, in the case where tx by ty is rational, we can consider a common period, and in that case we can define a cross correlation between periodic functions. There, the meaning of cross correlation is to take the product or the shifted version of the product of the shifted version of one function and the other over one interval, right? So we look at the quantity x t plus tau yt dt, the second complex conjugated, and divided by t, integrated over an interval of t. Yeah? You see, it's important to note that the integral here is over t, not over the whole real axis. Over the whole real axis, the integral doesn't converge. So there is no sense in talking about that and it's like this. See, what we are really doing is looking at the cross correlation between the functions after shifting them and then looking at it only over a period. And then you see, in effect, when we look at the Fourier transform of this, we are introducing periodicity again. The idea is, if you look at this quantity, it is also periodic with period t, right? So R, if you think of this as a function of tau, this is called Rxy tau, where x and y are, of course, it has the same notation. The only difference is that here Rxy must be interpreted as for periodic function. So Rxy is a notation which can be used either for aperiodic or for periodic functions, but one must interpret it correctly depending on the context. So when you are talking about two periodic functions, then the interpretation is as written here. Now it is very easy to see that this is also periodic with period tau. That is not at all difficult to show, because if you consider Rxy tau plus t, it amounts to replacing the argument here by tau plus t. And when you take t plus, so it becomes t plus tau plus t. So let me write it down. So when we have x t plus tau plus t, it's the same as x t plus tau, t plus, in fact it's the same as x t plus tau, right? If you think of this as an argument by itself, then x t itself is periodic with period t, so it's the same as x t plus tau. So it's trivially true that this is periodic with period tau. Now if it is periodic, then its Fourier transform shall be a train of impulses located at multiples of 1 by t. How do we get this train of impulses? Now we take, see, the same idea holds. You see, we carry over that idea from the context of aperiodic functions. If x and y were aperiodic, then this would be its Fourier transform. I am sorry, xf y bar f. Now we carry the idea forth from here. What do? We look at the spectrum of x and the spectrum of y. Now, please remember that the spectrum of x and spectrum of y are both trains of impulses because they are both periodic. But they may have different fundamental periods. For example, let's take an example. Suppose x has a period of 2 units and y, as I said, of 3 units. Then what would happen? You would have multiples, the frequencies that would be present in x would be at multiples of 1 by 2 units, right? So you would have 1 by 2, 1 by 4, 1, and so on. 3, I'm sorry, 1 by 2, 1 and so on, right? 3 by 2 and so on. And here I would have multiples of 1 by 3. So by 3, 2 by 3 and so on, right? 3 by 3, so 1 and so on. Now if I consider the two functions to be both periodic with period 6, what I am saying is that I must insert into this points at 1 by 6. So this is 3 by 6. So I have 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, 6 by 6 and so on. And one must think of all the other points on the frequency axis as having a 0 amplitude. So the Fourier component is 0 at those points. The same thing here. So this is 2 by 6. So 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6 and 6 by 6. So at all points which are not originally there in the spectrum, I make the spectrum 0. So the Fourier component is 0 at that point. Yeah. And now what do? The Fourier series or the Fourier components of the cross correlation are obtained by taking the product of the corresponding components of x and y complex conjugated. So for example, the 1 by 6 component for this cross correlation Rxy would be the 1 by 6 component here multiplied by the 1 by 6 component here complex conjugated. The 2 by 6 component will be this times the 2 by 6 component here complex conjugated and so on and so forth. Right? So the corresponding components, some of them might be 0, are multiplied and the second one is complex conjugated. That gives us the Fourier components of Rxy tau, which is also periodic, and then one can similarly put down the Fourier transform of Rxy tau as a train of impulses located at multiples of 1 by 6. Is that right? So it is very clear then that you will have components in the cross, the non-zero components in the cross correlation will occur only when both are non-zero. When there is a non-zero component in x at that frequency and a non-zero component in y at that frequency. Is that right? In particular, we could consider the autocorrelation of a periodic function. This becomes a special case of the cross correlation. Now here there is no problem. If the function is periodic, of course it's the same period t. So there is no problem. So what do? How do we find the Fourier transform of Rxx tau? Well, we have the Fourier transform of x, right? We have the Fourier transform of x located at multiples of 1 by t. So 1 by t, 2 by t, 3 by t, 4 by t and so on. Let us call them C1, C2, C3, C4 and so on. Yeah. How do we find the Fourier transform of Rxx tau? Needless to say, Rxx tau is periodic with period t, the same as the period of x. Yeah. So, how do we find the Fourier transform of this function? Well, we take the component at 1 by t and multiply with itself complex conjugated. So, what do we have? We have mod C1 squared, mod C2 squared, mod C3 squared, mod C4 squared and so on. That becomes the Fourier transform of the autocorrelation of x. Now, this quantity, as in the case of aperiodic signals, has a physical significance. In fact, this gives a measure, or this gives an indication of the distribution of energy in frequency, the distribution not of energy but of power across frequencies. You see, what is the physical significance of these quantities, mod C1 squared, mod C2 squared and so on? What is the total power? You are aware that the total power in a Fourier, in the total power in a periodic signal is the sum of the moduli squared of its Fourier series components. So, in fact, this gives us the distribution of power across frequencies, right? This gives us the distribution of power across frequencies. So, it is a power spectral density. This is called a power spectral density. This needs to be emphasized. When we are talking about aperiodic signals, we have an energy spectral density. When we are talking about periodic signals, the same thing becomes a power spectral density. It must also be very clearly understood that the impulses here should not be thought of as the product of the corresponding impulses in x and x. For example, when you talk about the impulses in Rxy tau, the impulse located at 1 by t should not be thought of as the product of the impulse in x at 1 by t and the impulse in y at 1 by t. No, it is not a product of impulses. We explained why last time. The product of impulses is not square integrable. Impulses are not square integrable. So, there is no sense in taking a product of impulse. It is not the product of impulses that we are taking. It is a product of the impulse amplitudes or the impulse strengths. So, what we are writing here is a square modulus of the impulse strength, not a product of the impulse with itself. This is to be distinguished. So, one should not think of this as mod xf squared. It is not really correct for the context of periodic signals. The context of periodic signals, it's not it's not correct to think of Rxy tau really as xf, the Fourier transform of Rxy tau as xf yf bar. It is not correct to think of them that way. It's a new Fourier transform, recognizing the fact that it is periodic and with impulses located at multiples of 1 by t, and the strengths of the impulses are products of the corresponding strengths. Now, this point needs to be emphasized in a first course, because it's a very common conceptual error that we perform if we are not careful, right? It has no meaning to square the modulus of impulsive transforms, right? Now, we proceed with this discussion to take the idea further. Can we have signals which have both periodic and aperiodic components? For example, let us take the case of the signal say e raised to the power minus t plus cos t. Right? What do we do with a peculiar signal like this? Or e raised, I mean, what I mean here is actually e raised to the power minus t ut. E raised to the power minus t ut plus cos t. So I mean that must be true only for t greater than equal, or the cos t part can survive for all t. Yeah.
Can you explain the previous part, sir, the difference between multiplying impulses and...
All right, the question is to repeat the previous discussion on multiplication of impulses and multiplication of strings. Now what I said is that if you look at the corresponding points, the point at 1 by t in the Fourier representation of x and the point at 1 by t in the Fourier representation of y, we get, so this is in x and this is in y, and both of them are periodic with period t equivalently. What I am saying is that when you take the cross correlation of x with y, there is a component at 1 by t, so in r x y f, there is a component 1 by t, but you should not think of this component as the product of this impulse with this impulse. Instead, it is of course an impulse here, but it is the strength of this impulse which is the product of the strength of this impulse and the strength of this impulse. It is not true that this impulse is equal to this impulse and to this impulse. A product of impulses has no meaning. It is not convergent, right? So we do not take a product of impulses, we take a product of the strengths of the corresponding impulse. So coming back to this, example, e raised to the power minus t ut plus cos t. Now let's find the Fourier transforms individually. E raised to the power minus t ut has a Fourier transform given by e raised to the power minus t e raised to the power j omega t dt integrated from 0 to infinity. This is integral from 0 to infinity j omega minus 1 . So that becomes e raised to the power j omega minus 1 t divided by j omega minus 1 from 0 to infinity. And that leaves us with 1 by 1 minus j omega. Oh, I'm sorry. Yeah. Sorry. I'm sorry. A correction. Yeah, I'm sorry. It needs to be corrected. So it's 1 by 1 plus j omega. All right. Now this is a continuous Fourier transform. I mean, it's a well-defined function of omega, no problem. What about cos t? You see, cos t can be written as e raised to the power minus jt plus e raised to the power jt by 2. So what kind of a Fourier transform does this have? This has a Fourier transform which is a pair of impulses at points 1 and minus 1 on the omega axis. Or you may say 1 by 2 pi and minus 1 by 2 pi on the f axis. And the strength here is half. So to be consistent, we could write both in terms of f. So what do we have here? We have two impulses located at 1 by 2 pi and minus 1 by 2 pi of strength half, right? And here we have a continuous function. In fact, it's an analytic function. Is that right? It's an analytic function of f. It has an infinity of derivatives. Now this kind of a signal is called a mixture signal. You can neither really talk about its energy nor its power. One can talk about the energy in a certain amount of time. In this kind of a signal, there is a finite energy in a finite time. That is quite clear. Right? There is a finite amount of energy in a finite amount of time. But in the literature on signal processing, or in the literature where we deal with signals, we do accommodate the Fourier transform of such functions. And the reason is we need to deal with such functions in the context of communication. For example, in the context of communication, one might be transmitting two things at the same time. One might be transmitting a sine wave, a pure sine wave, at what is called the carrier frequency. So suppose we have decided to transmit. Now we had seen the idea of amplitude modulation earlier. And we saw that the effect of amplitude modulation is to take the spectrum and shift it to around the carrier frequency. Now when we simply multiply the signal to be transmitted by the carrier frequency, cos omega c t, that kind of modulation is called suppressed carrier modulation. Suppressed carrier because the carrier is no longer explicitly present there. The carrier has been overshadowed by the message. Right? So now the message has already transformed the amplitude of the carrier. So it has overshadowed the message and we don't really see the carrier explicitly there. Now I explained this point to you last time. You see, I said that when you have a Fourier transform that has no impulses, then if you ask whether there is a particular frequency component present, the answer is no. If you ask whether there is a range of frequency components present, the answer is yes. So in the region where the spectrum is non-zero, you could talk about the presence of a range or the absence of a certain range of frequency components. But if you ask whether a particular frequency component is present, the answer is no. So in a situation where we directly multiply the message with the sine wave, with the carrier sine wave, we call it a case of suppressed carrier modulation. But for the purpose of reception, it is sometimes helpful to transmit along with this the carrier itself. So what do we do? What do we do in this case? For example, the Fourier transform of this function would be considered as the sum of these two Fourier transforms. The Fourier transform of e raised to the power, which is 1 by 1 plus j omega, plus this pair of impulses. So the Fourier transform would have a continuous part or an analytic part and an impulsive part. And one must interpret them separately, one must deal with them separately. Right? Now for example, in the context, as I said, of modulation, suppose you have a message or a waveform, a target waveform of xt to be transmitted. Then xt cos omega ct, right, where omega c is the carrier frequency, is the suppressed carrier part of the modulated signal. It's called the suppressed carrier part of the modulated signal. And we sometimes, this is so we call it, let's write it down, suppressed carrier. Yeah?
Can you please explain why it's called suppressed?
Oh, suppressed carrier, because you see, if you remember that if the spectrum of X looked like this, then the spectrum, if this had a unit amplitude at the maximum, the spectrum of xt cos omega ct looks like this. Is that right? Yes? Recall this? Yeah? Now, you remember last time that we said that when you have a continuous Fourier transform like this, suppose we ask, is there a component present at Fc? The answer is no. If you ask whether there is a set of components present around Fc, the answer is yes. But just as when there is a distributed transform, there is no component present at a particular frequency because the integral or the area in that particular at that point is 0. There is no area concentrated into a point. But suppose we add to this a constant A0 times cos omega ct. What happens? We get two impulses now of strength A0 by 2 located at Fc and minus Fc. So we get two impulses of strength A0 by 2 located here. And now this is called the carrier signal. This is called the carrier signal. So now we say amplitude modulation with carrier. And this sometimes helps, this kind of amplitude modulation helps because it allows you to recover the carrier at the receiver very easily by putting a very narrow band filter around Fc. So one can put a very narrow filter with center frequency Fc and retrieve the carrier. And why do we need the carrier at the receiver? Because if you recall, the process of demodulation simply involves multiplication. The simplest method of demodulation is to multiply this with cos omega ct and then filter. So it will be easier, instead of trying to generate the carrier at the receiver, it is sometimes easier to retrieve the carrier at the receiver from the transmitted waveform, right? And therefore we sometimes need to deal with this kind of a mixed signal. That is a part of the signal being an energy signal. So now we understand what we mean by an energy signal and a power signal, right? A power signal is one which has a finite power but infinite energy because of its periodicity. So we call periodic signals power signals, because they have a finite power but infinite energy. On the other hand, signals that are aperiodic and finite and have a finite square integral. Yeah, so signals that are aperiodic and have a finite square integral, that means the energy in the signals is finite, are called energy signals. So now we have two classes of signals and the nature of the Fourier transform is different. For energy signals, we have an analytic, normally not necessarily an analytic, but a continuous Fourier transform. For a power signal, we have impulsive Fourier transforms. A signal may be neither an energy signal nor a power signal, as is the case with this. And then the transform could have both kinds of components. A signal could be neither an energy signal nor a power signal and may not have a transform at all. For example, if you consider an exponentially growing signal e raised to the power of tut, its Fourier transform does not converge. So there is no point in talking about the Fourier transform at all. So once you lose the domain of energy and power signals, then you have no guarantee that the Fourier transform exists. It may or may not. Yeah. Now, to carry this discussion further, we need to look at some other issues. We are now going to bring in a new subject. We shall slowly introduce a new subject at this point. Now you see, we've been talking about continuous time signals and discrete time signals all this while. Yes, Amir.
Sir, what do you mean by retrieving the carrier signal? What do we retrieve?
Retrieve. The question is, what do we mean by retrieving the carrier signal? Retrieving means being able to just get the component A cos omega ct. So that can be done by, well, I am not going into the details here. Carrier recovery itself is a science, how it is done, but the basic idea is to put a very narrow band filter at the receiver.
So the amplitude is unimportant.
Amplitude is unimportant, so we need, but you see the problem is, but we need an impulse. So one cannot, so you cannot retrieve the carrier if there is no impulse in the, at the carrier frequency in the transmitted signal. So you see, one must be careful. You see, it's like, say, suppose you take xt cos omega ct. Since there is no impulse located at f equal to fc, at the receiver one cannot really recover or retrieve the carrier signal, because at f equal to fc there is no component concentrated. Why do we need to retrieve the carrier? Because we need to use that retrieved carrier for demodulation.
So we know omega c, fc we know.
So we can generate, see there are two ways. At the receiver one can generate cos omega ct with an oscillator, local oscillator, or one can retrieve the carrier from the transmitted signal. Now the problem with generating is, suppose you don't exactly know fc. Then you are not really, and also the other problem is, suppose you don't exactly know the phase of fc. The problem is, you may generate cos omega ct plus theta instead of cos omega ct, and then you are in a bit of trouble, right? Then you have, so then you can have trouble. So it's also important for the carrier that you generate to be as close in phase as possible. In fact, in the worst case, if your carrier is orthogonal, that means if your transmitted carrier is cos omega ct and your recovered carrier or the carrier generated at the receiver is sin omega ct, then your output will be 0. So you also need to worry about phase. So these issues, so when you go to a course on communication systems, these issues will become far more clear. But at this point it is important to note that when we talk about being able to retrieve a carrier, or when we talk about being able to get that pure component cos omega ct, it cannot be done unless you have an impulse located at that point f equal to fc in the transmitted signal. Alright. So now we come to an issue in the context of the Fourier transform. You see, the Fourier transform shall now serve as a bridge for taking us from continuous time to discrete time analysis. And we are going to build up this subject slowly in the sequence. Let us pose the problem first. We have been dealing all this while with continuous time signals and continuous time systems, and we have also been dealing separately with discrete time signals and discrete time systems. In fact, we call discrete time signals sequences. We call them sequences, right? Now, a natural question is whether there is a relationship between these. I mean, you may ask, how can there be a relation? There is fundamentally a different set on which the signals are defined. So what do you mean by a relation? Well, let me give a practical example. I wish to deal with a speech signal, right? So inherently, if I record the speech signal, it's a continuous function of time. What I hear, for example, from a tape recorder, or what I hear from a player, is a continuous time signal. Yeah. What I hear today from a computer which has an MP3 player is again a continuous time signal. It seems to be a continuous time signal. But you will agree with me that what is stored on the disk cannot be continuous time. In fact, it's just a sequence of zeros and ones. Right? So there's bound to be something discrete there. And somewhere there has been a transition from continuous to discrete in this whole process. Yeah? So, you see, the whole question is, suppose I have a signal defined on a continuous time axis, but for some reason I wish to deal with the signal using a discrete system, discrete time system. Now, you may ask, why should I want to do that? Well, the answer is that, you will study later, when you go to a second course on signal processing. You will study that there are certain wonderful things that discrete time systems can do, which continuous time systems cannot even approximate closely, or may only be able to approximate closely. So, discrete time systems have a wide variety of positive points. One of them is versatility. The other is flexibility, adaptability, robustness, and the ability to do certain things which continuous time systems cannot do. So, with this background, it becomes tempting to consider the possibility of dealing with continuous time signals using discrete time systems. You see, so what do we mean? I mean, how can you deal with continuous time signals using discrete time systems? Only if you can make the continuous time signal discrete in some fashion. Of course, you can make it discrete in some fashion. You can simply take its samples. So, for example, suppose you have a continuous time signal. I could simply take its samples. What do we mean by taking its samples? Well, we mean you're looking at values at specific points only. Right? And naturally, when we talk about taking its samples, then there are two possibilities. Either we can separate the samples with a uniform interval, or we can have non-uniform intervals between samples. But it is not really obvious why we should first consider the possibility of non-uniform intervals, unless there is a very good reason for it. So, let us begin with the possibility of uniform sampling. And what do we mean by uniform sampling? Have a uniform period. Let us call that period T. Having a uniform period Ts between samples. Yeah? How do we represent this operation mathematically? So what is this thing, what is this operation of sampling really? What should we do to describe that sample signal? Of course, it's a sequence. You can think of, that's right, yes. So you could think of how could you think of samples? You can think of them as impulses put at those specific locations. So you may visualize a train of impulses. See, you may visualize a train of impulses. The strengths of all these impulses are the same. Yeah, the strengths of all these impulses are the same. And what we are doing in the process of sampling is to multiply this continuous signal with a train of impulses. Yeah. Now, well, so far so good, that can be done for any signal, there is no problem. The question of importance is what happens in between the samples. So, once you have sampled it, have you lost something? On the surface, the answer is yes. I mean, you've lost what is in between. So whatever you do to those samples, it doesn't look obvious or it doesn't seem plausible that in general you are doing the same thing to the signal itself. Because it seems on the surface that you don't know what the signal is in between. That's obvious. But you see, here is where we shall now consider the possibility that we make certain assumptions about the signal. Let me give you an example. Suppose you know the signal is polynomial. Suppose you know the signal is polynomial. Suppose the signal is, in fact, let's take an extreme case. Suppose the signal is linear. Linear means it's a linear function of time, a plus bt. How many samples do you need to represent the signal? Only two. Two samples at two independent points. That's enough to represent the signal. So what is the situation? We have what is called some a priori information. So let's write that down. A priori. The word a priori means beforehand, right? It's prior, as you know, means before. So a priori means beforehand. I thought I should also introduce at this point the word a posteriori, right? Though it's not immediately relevant here, may occur in some other context, so it's helpful to introduce the word. The word a posteriori means afterwards. So posterior means after and a posteriori means afterwards. So a priori information means the information that you have beforehand. And now maybe we can ask the question, after you receive the samples, is it possible to reconstruct the signal a posteriori, right, afterwards? Now, in general, therefore, it is very clear that without a priori information, it is never possible to reconstruct the signal. That's trivial to show. If you have no information about the signal other than the value of the signal at the sampling points, there is an infinity of signals that can pass through those sampling points. I mean, for example, take this signal. You have these values at these points, right? And there is an infinity of signals that we can draw, in fact, a very highly continuous infinity, if you look at, if you see what I mean. Right? By the way, it happens that this infinity is even greater than the infinity of reals. So, you have an infinity of integers, that's a countable infinity. You have an infinity of reals, which is the next higher infinity. It's an infinity that is higher than the infinity of integers. And then you have this infinity of curves, so to speak, which is an even higher infinity. It's even higher than the infinity of reals. So the infinity of signals that you have here, which can produce the same samples at those points, is a very terrible infinity. It's an infinity even bigger than the infinity of reals. Right? Very bad situation to be in. But the moment we have a priori information, we can suddenly condense that infinity down to a single function. For example, suppose we know the function is a polynomial. For example, suppose, as I said, the function is a linear function, a plus bt. Of course, we agree that any two samples are sufficient. In general, if you have a polynomial of degree p, how many samples do we need? P plus 1. We need p plus 1 samples to reconstruct the signal. Now, these are very strong assumptions. Assuming, in fact, suppose the function is a sine wave. Suppose you know that the signal you are dealing with is a sine wave. Then, how many points do you think you need on the signal to reconstruct it perfectly? Suppose, let me make the problem easier for you. Suppose you know that the signal is a sine wave and you also know its frequency. That makes it very easy. Then you need only 2 points because you need to find the amplitude and the phase. So suppose so what I am trying to say is, suppose you have a signal, suppose you have a sine wave, suppose you know the signal is of the form a cos omega 0 t plus phi, and omega 0 is known to you, then you can see that if I have 2 different points, 2 properly chosen points t, which of course, what do you mean by properly chosen? They must not be separated by a period, and of course you can ensure that. If you know omega naught, you can ensure that they are not separated by a period, right? So you can then a cos omega naught t1 plus phi equal to sample 1, and a cos omega naught t2 plus phi equal to sample 2, right? And you should be able to solve for a and phi in terms of these. Is that right? Because these are 2 different angles, right? So in fact, if I take their ratio, I already get an equation on phi. And once I have found phi, I can find a, if I choose t1 and t2 properly. So it is very clear that just 2 points suffice. Alright? Now we shall take up this discussion further in the next lecture to see how we can reduce a priori information and then still increase the sampling rate to meet requirements. Right? Thank you. A couple of announcements before we depart. One thing